I hope you have your internet data with the changes one is there on your laptops. If it is there, please open this data. So we had to start with the second set of exercises. We finished the first set of exercises, if you remember, where we had to do the data entry, data cleaning, and descriptive statistics, cross tabulation, chi-square. This we all finished in the last class, and we understood what is p-value, we understood what is sampling distribution. So what I'm going to do today right now is I'll run a video on p-value so that any confusion about that concept is quickly addressed.
One of the most important concepts in statistics is the meaning of the p-value. Whenever you use Excel or other computer packages to analyze data, one of the key outputs is the p-value, or sig. In formal terms, the p-value is the probability that, if the null hypothesis were true, sampling variation would produce an estimate that is further away from the hypothesized value than our data estimate. In less formal terms, the p-value tells us how likely it is to get a result like this if the null hypothesis is true. We will now go through this step by step with an example. Helen sells choconutties. Recently, she has received complaints that the choconutties have fewer peanuts in them than they are supposed to. The packet says that each 200-gram packet of choconutties contains 70 grams of peanuts or more. Helen can't open up all the packets to check, as then she wouldn't be able to sell any. So she decides to use a statistical test on a sample of the packets. The null hypothesis, often called H0, is the thing we are trying to provide evidence against. For Helen, the null hypothesis is that the choconutties are as they should be. The mean or average weight of peanuts in the packet is 70 grams. The alternative hypothesis, called H1 or HA, is what we're trying to prove. The customers have complained that the weight of peanuts is less than what it should be. So the alternative hypothesis is that the average weight of peanuts is less than 70 grams. Helen decides to use a significance level of 0.05. If the p-value is lower than this, she will reject the null hypothesis. Having decided on her hypotheses and on the significance level, Helen takes a random sample of 20 packets of choconutties from her current stock of 400 packets. She melts down the choconutties and weighs the peanuts from each packet. If all of the values were lower than 70 grams, with a mean of 30 grams for instance, it would be quite obvious that the bars did not have the required number of peanuts. It is very unlikely that you will get 20 packets with a mean of 30 grams if the overall mean of all the packets in the population is 70 grams. Conversely, if all the values of the 20 packets are much higher than 70 grams, it would be obvious that there are enough peanuts and that there is nothing to complain about. However, in this case, the 20 packets contain the following weights of peanuts, and the mean is 68.7 grams. This caused Helen to ask herself, does this provide enough evidence that the bars are short of peanuts, or could this result just be from luck? She asks her brother to use Excel to find the p-value for this data, comparing with a mean of 70 grams. The p-value is 0.18. Judging from the data that we have, there is an 18% chance of getting a mean as low as this or lower if there is nothing wrong with the bars. That is, if the null hypothesis is true and the mean weight of nuts is 70 grams or more. This p-value of 0.18 does not provide enough evidence to reject the null hypothesis. In this case, Helen does not have evidence to say that the bars are short of peanuts. This is a relief. The smaller the p-value is, the less likely it is that the result we got was simply a result of luck. If the p-value had turned out to be very small, we then would say that the result was significantly different from 70 grams. In general, we start by saying that the null hypothesis is true. We take a sample and get a statistic. We work out how likely it is to get a statistic like this if the null hypothesis is true. This is the p-value. If the p-value is really, really small, then our original idea must have been wrong, so we reject the null hypothesis. P is low, null must go. A small p-value indicates a significant result. The smaller the p-value is, the more evidence we have that the null hypothesis is probably wrong. If the p-value is large, then our original idea is probably correct. We do not reject the null hypothesis. This is called a non-significant result. The p-value tells us whether we have evidence from the sample that there is an effect in the population. A p-value less than 0.05 means that we have evidence of an effect. A p-value of more than 0.05 means that there is no evidence of an effect. Sometimes a significance level different from 0.05 is used, but 0.05 is the most common one. Disclaimer. This video uses plain language to get difficult ideas across. Some terminology.
So I hope the p-value concept is to some extent clear, right? So in the last class, I was explaining about the sampling distribution. Sampling distribution is very, very important when we are doing hypothesis testing, right? We are today going to do the hypothesis testing for differences in means. Hypothesis testing, as I said in the last class, is of two types. One is hypothesis testing for association between variables, hypothesis testing for differences between means or medians. So that is what we are going to look today, hypothesis testing between means or medians. Now, for that, for me to begin explaining that, as I said, p-value concept is very important. And if you recall, sampling distribution was very, very important. How many of you are able to recall sampling distribution? I'll quickly tell once again what is sampling distribution so that we can proceed. There is no doubt, right? So let's say I want to get the average height of BTech students at IIT campus now. Let's say there are 5,000 students. I want to know the average height. I cannot go to each and every one and 5,000 students. So what I do is I obtain a sample of size 30 or let's say 35. I obtain a sample of size 35 each time. And let's say once the first time I obtained a random sample of 5,000 students, I have, let's say, list. I obtain random sample of 35 first time. Their average height is 5 feet 6 inches. Second time again I draw a random sample 5 feet 7 inches. Third time 5 feet 6 inches. Fourth time 5 feet 8 inches. If I keep on drawing infinite number of samples, I will get so many mean values. And if I draw these mean values on the y-axis, frequency, on the x-axis, mean. So I will get a curve like this, especially when the sample size is 30 or greater than 30, I will get a sampling distribution like this. Now what is the sampling distribution? When I drew infinite number of samples from 5,000 population of BTech students, 35 sample at a time. For each time I draw 35 respondents, 35 BTech students, I take down their mean and I plot that mean on this plot. So what is this? This is the mean of sample and this is the, on the y-axis is frequency. So every time I draw a sample of 35, I note down their mean. I keep drawing 35 sample from 5,000 students. I keep drawing infinite number of times. I keep getting means. Once I have these infinite means, I plot them on y-axis frequency, which means how many times a particular mean has occurred, and on y-axis the mean, what I got from the sample. So this is the curve which I will get. It is a normal distribution where the peak would be the population mean. Mu is the population mean, and most of these values will be within the 95%. They will be on the tails, it is 2.5%. So when I draw this particular curve for all the means that I extract from the population of 5000 BTech students, and my sample is 35 each time. I put the mean for infinite samples and draw this curve. I will get this curve, which is called sampling distribution. In the sampling distribution, y-axis is the frequency with which the mean in the sample is occurring. On the x-axis is the sample mean, and wherever I get the maximum frequency of means, the maximum time and number of a particular mean occurring, that is called the population mean.
Do you, when you're taking the samples, you have to take the same number of samples each?
Same number of sample each time. Yes. So this is the sampling distribution. If a sample is here, so let's say sampling the population mean is 5 feet 7 inches. This is 6 feet 9 inches. If a person is, if for a particular sample I find a value here, which means it is very unlikely because it is falling in 2.5%. There, so some of the samples are very, very unlikely to happen, because if the population mean is 5 feet 7 inches, it is very unlikely that I get a sample. Still it is possible because I got a sample. So when I plot this sampling distribution, this is plotting of the means of samples of size 35 when I draw 35 samples infinite number of times from a population. So this sampling distribution idea we are going to use in the hypothesis testing for differences. Now, how we will use this for the hypothesis testing? In the hypothesis testing, we start with assuming that null hypothesis is correct, and then we look for an evidence to reject the null hypothesis. So in hypothesis testing, there is null, there is alternate. We start with the idea that assume that null hypothesis is correct, then we look at evidence to reject it. For example, as I gave the example last time also, I just brag about my house, saying that in the backyard of my house there are thousands of coconut trees, with average height of coconut trees being 100 meters. Right? Now, some of you might accept it. There would be someone who is very smart who says that how could this be possible? I understand that he is our teacher, but he also cannot, he is expected not to lie. But here is somebody who is lying, who might be lying. But since he knows that I have been teaching with honesty, so he might think that it might be, there is some possibility it might be correct as well. So what he does is, or he or she does is, they create a hypothesis. Say null hypothesis is that population mean is 100 meter and alternate is not equal to 100 meter. So what that person does is, he assumes that null hypothesis is correct, which means assuming that the population mean is 100 meter, then he conducts the hypothesis testing. He or she goes and draws and goes to my house. Yes, they find that there are coconut trees, and he draws a sample of 35, and so he uses some machine to go up and down and measures the height. I don't know how. And 35 sample, and he got that the sample size is the mean height in that particular sample of 35 is 7 meters. Now we will come to sampling distribution to see whether to reject the null hypothesis or not. Now, assuming that null hypothesis being correct, which means assuming that the population mean is 100 meter, which means assuming that the population mean is 100 meter mu, how likely am I to get a sample with the mean of 7 meters? So let's say this is 100 and this is 125 meters and this side is 75 meters on the two tails. So I am getting a sample which is 7 meters, which is far on the left. This is 2.5%, 2.5%, which means the probability that I will draw a sample with such a less mean is very, very less than 2.5%. And if you actually, it will be very, very less, even 0.001%. That is the probability. So if the probability is such that it is less than 5%, assuming that the population mean is this, what is the probability of my obtaining a sample with a particular mean? If that probability is here or here, which means towards the tails, which means it is very unlikely. When it is unlikely that you obtain a such sample, you reject your initial assumption of null hypothesis. I am not saying it is not possible, it is possible. So we take this risk that with 5% chance that we may be wrong, the alpha error, 5% chance, but mostly 95% confidence we can say that null hypothesis is rejected. Still there is some error probability, right? Because if you draw a sampling distribution, you are likely to get some samples with on the tails. This could be one of the samples on the tails, but you accept this risk. To simplify, if you obtain a sample which is towards the tails and your assumption is that null hypothesis is true, as in this case null hypothesis is 100 meters, null hypothesis is that the population mean is 100 meter, and you get a sample which is very unlikely, then you reject the null hypothesis itself. This is what is the use of sampling distribution. So whenever the sample size is 30 or above, the sampling distribution will be normal distribution. You need not conduct any normality of sample type of test. But when the sample size is less than 30, you need to be sure that you need to conduct the test for the normal distribution of sample. But if the sample size is 30 or greater than 30, the sampling distribution will always be close to normal distribution. If the sample size is less than 30, you cannot say that the sampling distribution will be normal. Then you will have to first conduct the certain tests to look at the normality of the population, because the sampling distribution is likely not to be normal. So always the idea is always have the sample size 30 or greater than 30. Now let's move to certain tests for today that we have to conduct. First one is do the graphical and non-graphical tests to examine the normality of internet usage data. I assume you have your laptops and the sheets are open, you are not preparing for the quiz. Anyways, the quiz is whatever is going to happen will happen. You will miss this also and that also if you are preparing. So be present, as you know, all the meditation, yoga, mental health, all they say that focus on the present. Don't go into the future or look into the past. It will only worry. So the first one is do graphical and non-graphical tests to examine the normality of internet usage data. Now internet usage data sample size is 30. So we need not actually require doing it. But because there is a possibility in case you have the sample size less than 30, then you need to conduct this normality test whether the population is normally distributed. If the sample size is 30 or greater than 30, then you need not worry whether population is normally distributed or not, because sampling distribution will be normally distributed. But if the sample size is less than 30, you need to worry whether the population is normally distributed. So you need to conduct this graphical and non-graphical test for the normality of internet usage data. So we will quickly do it, although they are not very, very important, but we'll do it still. Analyze descriptive statistics. One is graphical test. You can choose either PP or QQ plot. If you click on them, you will get a window like this, and internet usage in hours per week. If you move to the variable box, just click OK. You will get a graph like this. If in this graph the points are close to the middle line, if they are close to the central line, very close, almost sticking to the central line, then you say that the normality assumption is met. Otherwise it is not. In this case, it doesn't look to be satisfied. Likewise, a QQ plot is also there. We will look at now statistical tests to do that, because this is just a graphical plot. You have to go to analyze, descriptives, explore, internet usage, move to dependent list, and statistics. Here, go to plots and click on normal plots with tests, continue, and so let me do it again. Analyze, descriptive statistics, explore, move internet usage into dependent list, click on plots, normality plots with test, continue, and OK. You are getting this tests of normality: Kolmogorov, Smirnov test, and Shapiro-Wilk. Kolmogorov, Smirnov, you have to look at if your sample size is greater than 2000, and if it is less than 2000, you have to look at Shapiro-Wilk. Anyways, when the sample size is greater than 2000, you need not worry. So Shapiro-Wilk is when the sample size is less than 2000. In this case, it is 30. We need not do these tests, but we are just looking at how and where to conduct this. So Shapiro-Wilk value is saying 0.001. What does it mean? It is we are inferring about the population that the internet usage data is not normally distributed, because 0.001. So what is the null hypothesis here?
Normally distributed. We are rejecting.
Yes. So there is null hypothesis and there is alternate hypothesis. What would have been happening in the background of the test? Null hypothesis is that the data in the population is normally distributed, and alternative, it is not normally distributed, right? Now, in the background, there is some calculations are going on regarding when you assume that assuming that null hypothesis is correct, then SPSS is trying to fit the data onto that particular line and seeing the difference, and thereby the p-value is being calculated. So the MBA student need not actually go further to think about what is happening at the background unless they want to specialize into data science, but the PhD student should actually, because this is very important. So this is what we did. We need not do it because sample size is 30. Now the next one is do a t-test to see the hypothesis that the mean familiarity rating exceeds 4, which is the neutral point. Or let me simplify it. Do a t-test to see the hypothesis that the mean familiarity rating is equal to 4. When I say exceeds, it becomes a directional one-tailed. I am looking at only positive tail. So do a t-test to see the hypothesis that the mean familiarity rating exceeds 4, which is the neutral point in 7-point scale.
So if it is not a normal data, then how we are using the t-test and all of those things?
That's what I said. 30 or greater than 30, your sampling distribution will be almost normal. And because we are utilizing sampling distribution for hypothesis testing, population, sample and difference, since that is close to normal, we could do these t-tests.
Here isn't it failing the Shapiro-Wilk test?
It is failing because the population is not normally distributed. It is showing, right? But we are worried about sampling distribution. If the sample size is less than 30, then we need to worry about, because the sampling distribution will also be not normal, and then we need to worry about the population distribution of the data. If the sample size is greater than 30, even when the population is not normally distributed, we don't worry, because sampling distribution will be close to normal and we could do all these tests. Most of the statistical tests we will be able to do when the sample size is greater than 30. Now the second one is do a t-test to see the hypothesis whether the mean familiarity rating exceeds 4. Let me simplify it. The mean familiarity rating is equal to 4. What will be your null hypothesis? Let me make it even simpler. Mean familiarity rating for example, let's say somebody works in Uber and they say please conduct the hypothesis test that our mean satisfaction of our customers on 5-point scale is equal to 4. Suppose this task is given to you. You will have to do it. How you will do it? That is what it is. If you are not able to see how it will be used in your job role, this is how it will be. What will be the null hypothesis? Nu is equal to 4, right? Alternate is nu is not equal to 4. It is a very equal to the same example that I gave. Mu is equal to 100 meters, right? So now there is a sampling distribution and you have drawn this sample of size 30 and you will see what is the p-value. How to do this? And I change equal to 4. Then we will come to exceeds 4. Let's do it first equal to 4. Which means it can be less than, greater than. Let's do the bidirectional. We will look at p value on both the tails, that it should not be either on the left side or the right side. So we'll go to analyze, compare means, and this is one sample t-test where we are comparing. There is one sample we are comparing whether it is the population mean is different from 4. So always when we are doing hypothesis testing, we are using the sample to infer something about the population. Sample is only one of the ways by which we infer about the population. So here compare means one sample t-test, you will get this window. Now we want to compare it with 4, whether the mean familiarity rating in the population is equal to 4. Mu is equal to 4. So familiarity we will move in the test variable, test value we will keep it as 4. Click options, don't do anything with it. Confidence level is 95% and you click on OK, you will get this result. One sample t-test. What is the significance two-tailed you are getting? Are you able to do that or shall I do it again? Okay, you have to go to analyze, compare means one sample t-test. In one sample t-test, the test value that you are going to test is 4, whether the mean familiarity is equal to 4. So your mu is, so as the Uber manager wanted you to do whether the mean satisfaction out of 5 is 4. So you put 4 here and draw a random sample and their satisfaction values. Let's say whatever is it, move it there and click on OK, and you are getting this test. This value, significance two-tailed 0.002. What does it mean? Assuming that population mean would have been 4, what is the likelihood of obtaining a sample with the mean? Here mean difference is given. What is the likelihood of obtaining a sample with the mean of 6.6? Here 6.6. 0.002 it is written. What does it mean? It is very unlikely, less than 0.05, which means you reject the null hypothesis. What was your null hypothesis? That a mu is equal to 4. Oh sorry, I did with internet usage. I'm sorry, I have to do with familiarity. Sorry. Previously, but I was sorry, familiarity 4 and okay. Yeah, so we are getting 0.011. Again, it is less than 0.05. So our null hypothesis was mu is equal to 4. And alternate y is not equal to 4. Then we ran this test and we are looking at whether this particular sample falls in the last two tails. And actually it is falling because the p-value, it is 0.011. 1.1% on the positive side, 0.011, which means less than 0.05, which means we have to reject the null hypothesis. It is not, in population mean is not equal to, in population mean familiarity rating is not equal to 4. Now, if this would have been whether mean satisfaction of customers, Uber customers is on a scale of 5 is greater than 4. Now we are looking at positive, one direction only, not negative. Then one way is, for one-tailed, whatever two-tailed value did you get, you have to divide it by 2. If you divide 0.011 by 2, what it will be? Divide 0.011 by 2. 0.005, and then you have to compare it with 0.05, because now you are looking at only one-tailed. 5% at one-tailed, whatever probability value you got from two-tailed, multiplied or divided by 2. That is the p-value for one-tailed test. Now the mean difference is positive 0.86667. And you see familiarity with the rating, mean is 4.8667 and mean difference is 0.8667. So you know what is there. You know that when the test would have been conducted, the first one is the sample mean, the second one is the population mean, the difference would have been taken, and the mean difference is positive, which means it exceeds 4. Because it is positive, towards the positive side. See, when is equal to 4, when we did with whether the mean familiarity is equal to 4, we rejected the null hypothesis, it is not equal to 4. Now, if it is not equal to 4, either it exceeds 4 or less than 4. And if you look at the mean difference, it is positive. And when this test is conducted, first is the sample mean minus the x bar minus mu, if you remember, x bar sample mean minus mu divided by s divided by under root n. So first comes the sample mean, then the mu. So if mean difference is positive, what is the meaning? Which means and p value is also 0.011 divided by 2, 0.005, less than 0.05. What does it mean? The mean familiarity rating exceeds 4. So if you will have to do with for this Uber, for your employees, whether their satisfaction, job satisfaction is this.
What is the utility of one-sided P here?
One-sided P is, so this is two-sided. When directional hypothesis is there, we only look at one side. So earlier this is 2.5%, 2.5% here. Now in directional hypothesis we look at 5% on either side. whichever side is the hypothesis made. So which means earlier it was only 2.5% area here, now it is 5% area. And this is mu is 4, this is familiarity rating 4, and this area is, let's say, 4.6, and your sample is somewhere here, or not somewhere here, 4.8886, which is in the 5% positive side. Mean familiarity rating exceeds 4.
Then if you already have one-sided P, then like why we need to divide the 0.011 by 2 to get?
Because that was two-tailed. In two-tailed, you have the 2.5% here, 2.5% here. Now in one-tailed, you look at all the 5% on one side.